Hey guys, today we're going to be talking about allosteric interactions. A significant portion of enzymes function such that their properties can be studied using the Michaelis-Menten equation, which is E plus S arrow K1 on top parentheses ES arrow K2E plus P. However, a particular of enzymes exhibit kinetic properties cannot be studied using the Michaelis-Menten equation. The rate equation of these unique enzymes is characterized by an S-shaped sigmoidal curve, which is different from most part of the enzymes, whose their rate equation exhibits hyperbolic curves. Allosteric regulation is the regulation of enzymes or other protein by binding an effector molecule at the protein's allosteric site. Effectors that enhance the protein's activity are referred to as allosteric activators, whereas those that decrease the protein's activity are referred to as allosteric activators, which as those that decrease protein's activity are called allosteric inhibitors. The term allostery refers to the fact that the regulatory site of an allosteric portion is physically distinct from its active site loops, such as feedback from downstream patches or feedforward from upstream substrates. The next thing we're going to be talking about is also the allosteric modulation, cooperativity. Cooperativity is a phenomenon displayed by enzymes or respiratories that have multiple binding sites where the affinity of the binding sites for a ligand is increased. Positive cooperative or decrease upon the binding of a ligand to a building site. We also see large claims of molecules made of many identical substances, such as DNA, proteins, and physical and phospholipids. Example of this positive cooperative is the binding of oxygen to hemoglobin. One oxygen molecule can be bind to ferrous iron of a heme molecule. In each of the four claims, chains of a hemoglobin molecule, deoxyhemoglobin, has a relatively low affinity for oxygen. But when one molecule binds to a single heme, the oxygen affinity increases, allowing the second to bind more easily, and the third even easier. The oxygen affinity of 3-oxyhemoglobin. This behavior leads the affinity curve of hemoglobin to be sigmoidal rather than hyperbolic as with the monomeric myoglobin. And we'll be also talking about the Hill equation, which you're going to see in your biochemistry test, which is very important to know because you have to know which the steps and the orders and what they all represent. So it's the degree of cooperativity is determined by Hill equation for non-Michaelis-Menten kinetics. The Hill equation accounts for allosteric binding at the sites other than the active site. So this is the equation. And this is what we're going to expect to see at the test. And I'll explain what all of these signs mean, like the L, the KD, the L, and then you have to times it with equals 0. Then 0 is the fraction of ligand binding sites filled. And L, which you can see in these parentheses, the L is the ligand concentration. K, and then you see the small k like D, like small kd plus L in parentheses, is the apparent dissociation constant derived from the law of mass action. Ka is the ligand concentration producing half occupation, and n is the Hill coefficient that describes the cooperativity. If you wonder why I'm talking so bad, it's because I just came back from swim practice like 2 minutes ago and I'm literally out of breath. So if you couldn't understand me, I'm sorry about that. Well, I was trying to explain, and there will be more parts about this allosteric interactions part. This was only the first part. There's so many more equations you can see in the test in biochemistry and so on, like that. Okay, thank you for watching, and I hope you liked the video. And I'm sorry if I speak bad because I was just in swim practice again, like 2 minutes ago. I just got out of the pool. So sorry about that, and I hope you have a good day, and God bless you all.